first of all, thank you. Thank you, Professor Somna Sarangi and the Department of Mechanical Engineering for providing this opportunity to interact with all of you. So the topic of my talk is on designing the futuristic dielectric elastomer based minimum energy structure actuator for soft robotics application. So during the lecture, I will don't make you a bore. We can have one-to-one interaction. In between, anytime you feel you have some question, you can just raise your hand. I can ask, or we can at the end of the presentation, we can have a discussion also. So let's start with the part. This is some quick outline of my presentation. I will show you some short introduction of the term. What is dielectric elastomer? What is dielectric elastomer based minimum energy structure? I hope you have already covered yesterday something about this dielectric elastomer. But still, I will give a quick overview and a quick glimpse of that, how actually it is working. And then I will take you to its application. That is the most important part, how we can implement this soft active material for different soft robotics application. Because I am telling you very frankly that nowadays, these three fields are very, very trending. First, you all know the artificial intelligence and machine learning. The second is additive manufacturing. People are working very like in a very dramatically way or a drastically way in these fields. And the third one is this soft robotics. They all have their unique advantages. That's why people are shifting towards this, their application. So let's come to that. So this process that I have learned during my postdoc from Germany is very, very simple. They says that whatever you are doing, you should have a great motivation behind doing that thing. So I always, whenever I am presenting this work, I always keep my first slide as a motivation. Why? Why we have to move toward this soft active material, soft robotics. So if you see in our day-to-day life, most of our motivation we get from our mother nature. You see, when you see your body, God has created our body, a lot of engineering are there. So after seeing the movement of your hands and after seeing like your nearby things like the fish, if you go to the river, you see the fish, octopus, so a lot of different things that is available in the nature, different types of flowers, fruit, they all are the creation that will give you a motivation that what is the mechanics behind it? What is the physics? How it is working? So always we get motivated from our mother nature. So in the field of soft active material also, why people start working in this domain? Because they see that a lot of things that surround us, they have some actuation capability, they have some moving ability. So people says, can we develop such type of abilities in the artificially tuning material? Can we tune such material so that we can have biomimic their response? And the answer is yes. We have the soft active material that will help you in biomimic the response of your muscles, in biomimic the response of natural organisms. A lot of things you can do. So one of the motivation I have shown you here, it is the octopus arm. You can see octopus arm is without a skeleton structure. There are large number of muscles that coordinate together. You can see from the schematic. So when an obstacle comes, they will coordinate together, they will contract, and after passing through that obstacle, they will expand. So what is happening? These muscles basically are controlling their movement without a skeleton structure. So we say that we can also develop some type of system like this in which no linkages, no kinematic links, and no joints will be there. Can we have? Yes. Answer is yes. By using the soft active materials, we can develop such type of actuators which can biomimic the response of such type of natural organism. The thing is, always the coin has a two aspect. One is a positive, one is the negative. So the positive aspect is we can get larger degree of freedom when we are using this soft active material. We can obtain very large deformation or actuation by using this soft active material. And they have a very quick response to the diverse external stimulation like magnetic field, electric field, a lot of fields we can apply. And the different types of soft active material can respond to that actuation field. Okay. I hope motivation is clear why people are moving toward this soft active material. So after getting motivated from the mother nature, so we says that now people are moving towards this. I have already discussed. The thing is because this soft active material can easily biomimic the response of different types of a system that you see. So you can see one of the flexible pneumatic actuator by applying a pressure, you can have the actuation capabilities. You can see a gripper. It look like your hand. So you have the different fingers that can be used for holding or gripping an object. This all can be developed with the help of this soft active material. So that is a great motivation for the society or the scientific community that yes, nowadays we should start exploring this soft active material. The major thing is that, for example, in the space application, all of you have seen the Mission Mangal movie. What is the point? Weight consideration. They always try to reduce the weight so that after reducing the weight, they can, in the less fuel, they can reach to a particular destination. So this soft active material is very less in weight. We can get a larger flexibility, degree of freedoms, and actuation capabilities. That's why they are being nowadays recently implemented in various space applications, in the sea marine application, in the gripping application. So I will show you one video also where how can we easily implement that in the soft gripping application also. So after getting motivation, you can see at the international level, one of the greatest example is the MIT University. They have developed the soft fish. So if you see their actual fish, this is a demo of that initial demo. So you cannot make a distinguish between the actual fish and the artificially developed fish that is made of soft active material. So that's the way the international community has taking this level to a next level. Okay. So Duke University has developed dragon type of butterfly. So you can see dragon type of prototype in which we can have the response of a dragonfly. So the motion of a cheetah can also be replicated by using the soft active material. Now, the important thing is how we can classify them. It's a very simple way. Since they are getting actuated when we apply the external stimulation. So the external stimulation will going to govern the different types of the soft active material. For example, if I apply electric voltage, then it is classified as electroactive polymer. If you apply magnetic actuation, it will call as magnetorheological elastomer. So the different actuation like magnetic field, electric field, application of the different temperature, chemicals, pressure difference, all these things will govern or will classify the material, soft active material into a different class. So based on the actuation field, we can have different types of soft active material. So in this presentation, I am discussing only about this electroactive polymer, that is dielectric elastomer. So yeah, anything, any query?
No, I think someone has not muted.
Okay. Okay. So I will tell you frankly, this principle I have learned during my postdoc from Germany. There, people are very strict about the three things. They says whatever you are doing in your life, in your research, in your academic area, first ask three questions to you. They follow the principle of WWH. So first W stand for what, second W stand for why, and third W stand for how. First ask yourself what you are doing. Even in your life, you can implement this thing. So first other material. If you are successfully able to answer all the two questions, then you ask how we can develop this dielectric elastomer based actuator or devices. So I will start with the first question: what is dielectric elastomer? Quick overview, because already you have, I think, understand in the previous sessions this thing also. So this dielectric elastomer is an elastomeric film sandwiched between two compliant electrodes. So when the potential difference is applied, you can see between the two compliant electrodes. So what is happening? A positive charge will get accumulate on one of the electrode, and the negative charge will get accumulated on the other electrode. So we know the basic physics: the opposite charge will attract each other, and at the same time, the same charge will repel each other. So because of an electrostatic force of attraction, the membranes start compressing in the thickness direction. And at the same time, the same charge, because of the repulsion, so the membranes start. So you can see from the graphic also that how it is working. When the potential difference is applied, membrane will compresses in the thickness direction and expanding in the aerial direction. So this deformation has been reported to reach well beyond 400%. It's a very large deformation. So this is dielectric elastomer. We understand what is dielectric elastomer. So it's a type of electroactive polymer. Because we apply the electric field, it gets actuated. Now we can implement this unique characteristic of undergoing large deformation to the different application. I have shown some of the application. It is very interesting application. By using this dielectric elastomer, you can develop simple bending actuator. You can biomimic response of your eyes. You can biomimic response of your human heart by putting the something reflective material over the dielectric material. So you can develop some tunable lenses. Okay. So these are the different ways in which we can implement this dielectric elastomer for different application. Now, every coin, you know that every coin has a two aspect. I have discussed all the positive aspect, but there are some, instead of saying a negative aspect, I can say the challenges. So this dielectric material, this dielectric elastomer membrane exhibit strong material non-linearity. Why material non-linearity? Because they typically exhibit viscoelastic behavior. Okay, this is true for this acrylic elastomer. They exhibit strong viscoelastic behavior. So what is happening? It will lead to a strong material non-linearity in this dielectric membrane. They have a very strong electromechanical coupling. So when you apply I have already said that we are going to apply a potential difference over the two electrodes. So there is definitely a threshold limit. After the particular application of increasing the voltage or the applied potential difference, the breakdown of the membrane will take place. So that breakdown sometimes refers to as pull-in instability, and other type of instability also occur in this dielectric elastomer. And they also require a very high voltage to get them actuated. So these are basically not a problem. We can say that these are the challenges. We need to incorporate these challenges in this dielectric elastomer, and then we can utilize them effectively in the required application. So my first question that should be come to your mind, what is dielectric elastomer, is clear. It is a simple elastomeric film that is working on the principle of electroactive polymer. Now the second question is also very much clear. Why? Because it has a lot of advantages. In compared to the other conventional material, this dielectric elastomer possesses a lot of advantages. That's why we have implemented them for the different application. Okay, so I will show you a very interesting application of this dielectric elastomer. So we are implementing this dielectric elastomer in a minimum energy structure concept. So what is this? Again, the question should be what is dielectric elastomer minimum energy structure? So you see, it is basically a complex 3D equilibrium configuration characterized by the minimum energy state of the system. So now it's a name suggesting that a system that is having a minimum energy is termed as the minimum energy structure. Since it is made up of dielectric elastomer and a frame, so it is called as dielectric elastomer based minimum energy structure, DEMES. Okay. So what is this? We are having a dielectric membrane. Okay. This is a dielectric membrane with us. It is in the pre-stretch state. So initially we pre-stretch the membrane because it has a lot of advantageous effect. Then we are having a frame, compliant frame. So that frame is not something unique to you. You are using transparent file. You are in day-to-day life, you are using a transparent file. So that is made up of PET material, polyethylene terephthalate material. Take that material, cut that material into a particular shape. You will have a shape of a frame, then put it over the pre-stretched dielectric membrane. So this dielectric membrane is pre-stretched. So what does that mean? It means that it will have some energy, strain energy stored in it. So because of the stored strain energy, when you put it over the frame, over the surface, and you cut it, remove it with the external mechanical constraint. So it is not just put it over, we are having a mechanical constraint like some spring type of structure also. I will show you that thing also. And when you remove it with the help of a razor blade, so the entire configuration will try to attain a configuration that is characterized by the minimum energy state. So in this universe, everybody wants to be stable by minimizing their energy. So this structure is also simple of that. It is the initial configuration in which no potential difference is applied. Now in the second case, we are having a dielectric membrane. So we put active area by putting carbon grease and we applied the potential difference. So when we apply the potential difference, so what is happening? Again, the strain energy will get stored in the membrane. So it will try to bring the structure to its original configuration. So this is the initial configuration. This is the final or actuated configuration where structure try to go back to its original shape. So we can use this principle of DEMES in developing different application like gripper. Initially, when we preset and release it, it will hold an object like this. It is holding an object when no voltage is applied. Now you apply the voltage. When you apply the voltage, structure try to go back to its configuration, initial configuration. So it release the object. Again, you keep the voltage zero, it will again hold the object. So similar way, we can have the flapping wing, in which when you are basically not applying the voltage, it is being at a particular configuration. When you apply it, and you're applying a cyclic loading, it will keep on actuating. So this is the way we can implement the dielectric elastomer in the minimum energy structure. And I will show you today that this DEMES can be implemented very actively in the different soft robotics application. Now, again, the challenge is that earlier this dielectric membrane has a strong material non-linearity. Now we have incorporated frame also attached with it. So this DEMES have a material non-linearity as well as geometrical non-linearity. Geometrical non-linearity arises because of the coupling of the frame with the membrane. Okay. So let's start discussing how we can have this development of dielectric elastomer in the different configuration, different soft robotics application. So I have started during my case study, I have started with a very simple bending actuator. We are a lazy person. We always start with a simple thing. I'm just joking. We start with a simple thing and then we extend to a complicated application also. So for developer simple, we have considered simple rectangular type of compliant frame. So this is actually, this is frame, this frame. So we start with a simple rectangular compliant frame, okay? And it is hollow at the central position. Then we are having a pre-stretch membrane and we put this membrane over the structure. So it look like this. And when we cut it from with the help of a razor blade, so it will obtain a configuration like this. So this is the analytical formulation we have done. Okay. So just a quick overview that how we can model this problem. So I will tell you one important thing for solving any engineering problem. This is like a guru mantra, you can say. For solving any engineering problem, okay, there are three different approaches out there. The first one is the analytical approach. Okay, that is called as the exact solution that will give you an exact solution. Analytical approach is there. Second is the numerical approach that will give you an approximate solution. And third one is the experimental. So accept these three approaches. If you know any one of this approach, you can solve a problem. Okay, so I will show you the glimpse of all the approaches, analytical, finite element, as well as the experimental. So this is the analytical approach that we have implemented to solve the problem of this viscoelastic property in the dielectric elastomer based minimum energy structure. Why viscoelastic property? You see, this exhibits strong material non-linearity. So material non-linearity arises because of its inherent viscoelastic behavior. They exhibit a very strong rate dependent properties. That's why this material non-linearity creep in. So we need to tackle this because it is a challenge we have to incorporate. So this is the structure will look like when we release it from the external constraint. So we are having a two part. One is the frame, one is the membrane. Okay. And this is the angle. For example, if you have a rectangular frame, you provide it over the pre-stretch membrane, cut it. So it will attain a configuration like this. So from the horizontal, it will make an angle called theta. So that theta is important for you. What is the angle? Equilibrium angle it is make. And when you applied voltage, how much it go back. So that two things are very important for you. So what is our concept is the frame is going to bend like this. So what is the frame bending energy? We can calculate by using a simple constitutive mechanical model, m square dx by 2ei. And in case of a membrane, it is a pre-stretch membrane. So we are having a different types of hyperelastic material model available, like Neo-Hawkian, Moni-Rivni, a lot of models are there. So we have taken the simplest model, Neo-Hawkian. Why simplest model? Because you can see in the further slide, if we are taking even the simplest model, our equation of the motion are very, very complicated. So if we take, it is a general model, we can extend to any available hyperelastic model. So we started with a simple model, Neo-Hawkian model. So we will have the membrane strain energy, okay? We will have the frame bending energy. So we can calculate now the total potential energy of the DEMES. So total potential energy will be the sum of frame bending energy plus membrane strain energy. And again, this membrane exhibits strong membrane viscoelastic behavior. So to incorporate this viscoelastic behavior, we have implemented a simple standard linear solid model. That is Zener model. What is that Zener model? It comprises of Maxwell element connected in parallel with a spring element. So this is called as Zener rheological model. So why it is implemented? To encounter or to incorporate the effect of membrane viscoelastic behavior. So when you incorporate this, you can see you are having isotropic equilibrium part as well as isotropic viscous part. So that basically is going to help you in calculating or evaluating how your membrane viscoelastic behavior will govern this attained initial angle and the final angle of the DMS actuator. Okay. Now, since you can see that this entire system can behave like a single rotary joint. So we will have a kinetic energy as half I omega square. Now you have potential energy with you, you have kinetic energy with you. Now just implement the Euler-Lagrange equation of the motion, because Lagrangian is nothing, it is the difference between kinetic energy and potential energy. So those who are familiar with these things, they know that how we can implement Euler-Lagrange equation of the motion. So we have everything in terms of the theta. So we have the Euler-Lagrange equation of the motion in terms of theta. So by putting this value of potential energy, kinetic energy, we obtain this complex non-linear dynamic governing equation of the motion of the DMS actuator. So that is one thing. Second thing is that lambda viscous is here. That is an internal variable that come into picture because we are incorporating viscous effect of this membrane. Again, implementing the Euler-Lagrange equation of the motion. Now with respect to lambda viscous, instead of theta, with respect to lambda viscous, we obtain again an evolution equation of the DMS actuator. So we are having the one governing equation, one evolution equation. And what is the initial condition? When the membrane is attached to the frame, theta is 0. Initial at time t equal to 0, theta is 0. Okay. So these are the initial condition. Theta is 0, d theta by dt is 0. And lambda viscous is basically nothing. It is, we are considering initially equal to pre-stretch of the membrane, lambda p. So we are having this analytical formulation with us. Now we can use a MATLAB ODE45 solver. So that's a very good inbuilt solver. You can directly implement. I will share you the code also if you want. So in that MATLAB ODE45 solver, basically 45 means it's an RK method of fourth order. Okay. So we feed these equations along with the initial condition and we try to analyze the effect of membrane viscoelasticity. So that viscoelastic effect is governed by the viscosity parameter eta. So you can see as we keep on changing this viscosity parameter, our attained initial angle of the structure have a significant effect. So your membrane viscous elasticity, if it is large, if it is small, it is going to govern the attainment of your attained initial angle. As well as the final angle when you apply the voltage to that, electric voltage, it will also govern your attained final angle. So what it shows that, yes, there is a material non-inerty because of the viscoelastic behavior of the membrane, but we can tackle it by implementing the analytical formulation. We understand, we have the concept that if we have a membrane of this much viscosity, it will take that much time to attain the equilibrium angle. Or if we have the membrane of different viscoelastic property, so it will take that much time to attain the equilibrium angle. So that is one thing. Next thing is, nowadays, if you see, you already know that the scientific community are working largely to incorporate the anisotropic effect. So either in composite or in the different material. Basically, the elastomer is also a one of the classification of the polymer matrix composite. So we are having the elastomer, that is dielectric elastomer. So what we put a reinforcement on this dielectric elastomer. So why we put this reinforcement, or you can also have a clear visualization. I hope all of you have played the card once in your life. You play the playing card. So think about that. You are having a playing card and you put a rubber over its surface. So what will happen? It will try to bend the card like this. Now, if I say that rubber is of higher strength, so when the rubber is of higher strength, it will try to bend the card more. Similar thing, we anticipate that if we need a large equilibrium angle in case of a bending actuator, so what should we do? We put anisotropy reinforcement in one particular direction along the length direction of the elastomer. So what it will do, it will try to bend the structure more. Okay. And as we keep on increasing the strength of the reinforcement, our structure will keep bending more and more. So that we can control by incorporating anisotropy in the dielectric elastomer membrane. So that we have done. So now our strain energy will have isotropic part, anisotropic part, and electrical part because we apply the voltage to that also. So I'm not going into detail, just a quick overview that we can have a simple membrane and we can have a membrane with the reinforcement also. So our total potential energy will get now modified because of the incorporation of the anisotropic part. And you can see as we keep on increasing the anisotropy parameter, xi here is a anisotropy parameter that represents the strength of fiber reinforcement in the direction of the fiber. So whatever the fiber you have incorporated, the strength of that fiber or the reinforcement is basically governed by this parameter xi. So you see when we keep on increasing this parameter xi from 0, 1 to 6, this is attained equilibrium angle, it keep on increasing. That is we are anticipating. By taking a very simple example of a playing card, we can anticipate that thing. So we are getting the exact results or we are getting the quite right trend that we are anticipating. Now, as we keep forwarding, so it's like always, we start with a very simple thing, but we always face some different type of problem or challenges. So what we see when we have a pre-stretch membrane at the frame in the DMS actuator and we release it, so they exhibit warping. Warping is what? It is out of plane deformation. So that is basically the property or the phenomena that we don't want. Because if there is a warping at the tip side, out of plane deformation at the tip side, and you are using this for gripping application, it will not have a proper gripping of the object. So we say, yes, it is a problem. We have to tackle it. So in order to alleviate this warping effect, we have developed an idea that if we put stiffeners on the surface of this compliant frame, then what is happening? What will happen? Definitely the warping at the tip side towards the frame side will keep on reducing. And after validating it with the finite element simulation in Abacus, we obtained that yes, because of the incorporation of the stiffener, you can see there is a complete elevation of the warping when the stiffener are incorporated. Okay. So we have a problem, but we are engineer. Basically, we all are BTech. So we are as an engineer, we have to find a solution for that. So we find a very simple solution. Let's put some stiffener over that. So that putting of stiffener, you see, that is not only the one reason. One reason is that warping is completely elevated. Second reason is that when you are using for the gripping application, you need some stiffening element there. You need some stiffening effect so that it can properly hold an object. So that stiffener also provide that holding stiffness to the DMS actuator. And third thing I will show you that we can orient this stiffener at a different angle to obtain different modes of deformation also. Now what is happening? Your total potential energy it comprises of a frame, it comprises of a membrane, it comprises of a stiffener. So this is frame, this is stiffener, this is membrane. So your equation of motion become very complicated. But what you can do, you can change the distance between this consecutive stiffener. You can play with it. You can change the material of the stiffener. You can change the geometrical dimension of the stiffeners. So that will give you an effect, but your warping will get elevated. You have a problem, you solve that problem by putting stiffener on the surface of DMS. Now, but we should have some confirmation with the experimental that whether what we are obtaining, it is actually we are at the ground level we are getting or not. So for that, we have conducted some experiment on the DMS with the stiffener. So this is, we have proved that this by putting stiffener, we will get a completely warping elevated structure. So we say that, okay, we start with that. So we have this DMS with different spacing between the consecutive stiffener. And when we release it, we obtain the different attained equilibrium angle because the spacing between the consecutive stiffeners are changed. This is the experimental modeling we have done. This is the mechanics, how we have followed this. General experimental setup, we are having the pre-stretch mechanics. After pre-stretching that mechanism, and we are putting all this stuff like compliant frame, stiffener, carbon grease, copper tape, etc. Okay. So we obtained this structure. Now, in this structure, we have to measure what is the attained initial angle from the horizontal. Okay. So, hello, is it audible? Can anyone confirm? Am I properly audible?
Yes, sir.
Yes, sir.
Yeah.
Audible, sir.
Thank you. Thank you so much for the confirmation. Okay. So for measuring this attained initial angle, we have developed an image processing technique. Okay, as an engineer, you always face a problem. But you are researcher, you are engineer, you have a mind of an engineer. So always try to find a solution for that. If we measure manually, definitely an error will creep in. So what we have done, we have developed an image processing technique in the MATLAB. So what we are saying, we take an initial image, filter out that image and measure that angle by using that image processing technique. So it will give you an exact equilibrium angle, what you are getting from this image. Okay. So we compare this experimental obtained part with the analytical solution we have here. Okay. More or less it is matching. The trend are almost good. But for the some of the cases, for the higher pre-stretch level, it is little bit not matching. The reason is a lot of source of error will creep in because manually we are putting carbon grease over the surface of the dielectric membrane. So that is one source of error. Second source of error is I have said that this membrane exhibits strong viscoelastic property. But in this model, we have not incorporated this analytically because it become very complicated. So that will be the source of the error. But we know that our trends are matching quite well. That is the experimental part and the analytical part. So we say that yes, the developed model, this analytical developed model can accurately predict the electromechanical response of this DMS actuator because it is matching with the experimental part. So now the important thing is, we move forward. This type of actuator that we are considering DMS actuator, they are, when we are taking them onto the actual level, they exhibit inhomogeneous deformation. But in all the analytical expression, we consider that they undergo homogeneous deformation. Analytically, it is very, very tedious and a difficult task to incorporate inhomogeneous deformation in the membrane. But there is a tool. I always say that there are three different ways. One is the analytical, one is the numerical, and the third one is the experimental. So there is a tool called finite element. So we can implement that finite element to incorporate the inhomogeneous deformation of the membrane. So how inhomogeneous deformation incorporates a very, so we have the tangent modulus. Instead of a simple modulus, we will have a tangent modulus that will going to vary along the entire material of the membrane. So we use finite element simulation. We use Abacus software. In Abacus, we develop a user-defined element. Okay. Why user-defined element? Because in Abacus, we don't have an inbuilt electromechanical coupled element. So we have to define an element that will have an electromechanical coupling. Okay. We use a coupled problem, entire coupled problem. One is the mechanical domain, one is the electrical domain. I am not going into detail to that. We have used Abacus software with the user-defined element subroutine to develop a finite element simulation of the DMS actuator. So this is the element that we have developed. It's a 8-noded continuous brick element. It is having a 4 degree of freedom at each node, 3 mechanical and 1 electrical displacement. Okay, so we match this. For example, if we consider single element and we apply the voltage, so we match with the experiment, like analytical expression, it is giving the quite good expression up to a particular stretch level. Okay, then we implement this element, this develop element for the finite element simulation. So you see that we obtained again a good match between the finite element simulation and the experimental part. So always we make a comparison with the experimental. The reason is the experimental is the actual thing that we have to be at the ground level. So whatever we are obtaining, that should be matching with the other tools that we are developing. So we obtain also a good trending match with the finite element simulation with the develop and experimental part. Then we say that why we are considering only rectangular shape of the electrode and the frame. Okay, we can change the shape. We can change the shape of the frame as well as we can change the shape of the active area of the electrode. So we consider 3 different shapes like rectangular, circular, triangular. Or in this one, we also change the area. In the rectangular frame, we have the circular electrode, we have the triangular electrode. To obtain the different types of attain initial angle and the final angle. So you see that when we change the shape of the electrode and the frame, we have the different attained angle. Okay, we have the different attained actuation stroke. Actuation stroke is nothing, the attained initial angle and when the voltage is applied. So how much it goes back, that is basically called as actuation stroke, or the we can say that it is representing the actuation range also. Okay, so we have this different shape. For this, we obtain the different tip angle. Now come the important part. We have started with that simple analytical formulation of the bending actuator. So at the bottom, you can say. Then we put the stiffener over it. Why? Because we seen that there is a warping. To alleviate this, we have the stiffener over that surface. And we develop the experimental part for that, because that is the important thing that we have to implement. Now we say that let us take to this all the developed framework to a advanced level. So what we have done, we now look into the our nature. So we have this dragonfly. Actual dragonfly will look like this. Okay. So we make some idealized shape. We say that this is an idealized shape for that. And the develop finite element model here, it is being implemented for the development of this DMS based dragonfly. Then we conducted this experiment to basically biomimic the response of this dragonfly. Again, we obtained a very good match. We are obtained this thing. So what is the practical application? You all can think about the practical application. We all have seen that Uri movie. Okay. So there is a Garud will be there that went to that for the spy application. But it got that one of the child there, he tried to catch that Garud because it is visible. If we can develop this type of system, very small type of object, or you can say unmanned aero vehicles. Okay. So very small, we integrate some small camera over that. and it can fly and it could go particularly. A lot of things to be done on this. We are getting a simple actuation of that. But if you put it like this, we can use it for the spy application. Okay. So that is the one of the greatest application I am looking for that. We are integrating all this thing here at our lab. So we start with a very simple bending actuator. We extend it to the development of the real type of structure that we see in our nature, like dragonfly. Okay. So that is the work that I have carried forward during my postdoc in Germany. So the concept is we have seen that most of the people are doing what we also doing like that initially. We have a simple shape of the actuator. We take a simple shape like square, rectangular, or circular. Like that, I have also taken simple shape of the rectangle. So what people are doing, they will club them. They form a three type of rectangular actuator and then club them. They are combining them to form a different structure, like flapping wing. Here they are trying to replicate the motion of a frog type of actuator. So what is they are doing? They have developed 1, 2, 3 and club them. They have 1 or 2 and then they club on a common body. So what is happening when the voltage is applying? So the failure will always, the more, this is more susceptible, where the joining of this different simple bending actuator are being clubbed together. So the instability or the failure will more, these areas are more susceptible and has a more chance of getting failure. So I developed an idea that yes, this trade-off can be given away. Why we are developing different single actuator and then clubbing them together? We can have a single compliant frame having the actual shape of the structure that you want. That is quite feasible. So what I have developed an idea that we can have a single compliant frame having the actual shape of the DMS that you want finally. So you can see in this, there is a single compliant frame having a 4 leg. So we cut it actually like this initially. One approach is we form the 4 different finger and then club together on a single platform. But that area will become susceptible. If you have a single structure that already has a 4 leg, then we implement it over the pre-stitch membrane and we obtain the configuration. Then we are less susceptible to the failure at this particular prone areas. So that this idea is being developed. And we have developed different complicated shape of this compliant frame, put it over the pre-stitch membrane, and we obtain the different configuration like 4-arm gripper. You can see it from here. So that 4-arm gripper, if you see, basically we have carried out experimental part for that also, as well as finite element simulation. Now, one important aspect I will tell you, very, very important. The key parameter is the pre-stitching of the membrane here. So the larger you are providing the pre-stitch to the membrane, so what is happening? Because of the pre-stitching of the membrane, the energy will get stored in the membrane, strain energy. So when you release it from the razor blade, so the larger the pre-stitch, you can see here, the larger your finger will bend or the structure will bend. Why? Because membrane posing larger energy towards the frame to get it bent. And the other important parameter is the frame bending stiffness. If the frame has a larger bending stiffness, it will try to resist that bending. Smaller the stiffness of the frame, it will go more bend. It will bend more. So two main parameters are there: pre-stitching of the membrane and the frame bending stiffness. So as a researcher, as an engineer, we have this ability to tune this thing. We can decide whatever the pre-stitch we want. We can decide the material of this compliant frame, like either a frame having the larger stiffness or the frame having the lower stiffness. So based on that, we can optimize the attained initial and the attained final configuration of this DMS actuator. So this is the simulation part I have shown to you that we have carried out in the abacus. Now we have also taken, apart from this flapping like 4-arm gripper, we have also developed this DMS based flapping wing actuator. Very, very interesting. So I've already told you that the stiffener, incorporation of the stiffener will not have only the single effect. It will also have an effect like we can put this stiffener. Okay. Why we are putting the stiffener? Because if we are not putting, we will get some warping at the tip side. Okay. That is one concept. When we put the stiffener, then warping is completely elevated. Okay. That is another thing. Now the important thing is we have already known this thing. If warping get elevated, that's fine. But can we orient that stiffener? Because actual flapping will not have this bending motion only. They can have bending and twisting, combined bending and twisting motion also. So we says that yes, no problem. We can orient that stiffener at a particular orientation. So when we orient this stiffener at a particular orientation, so what we will get? So we will have the, along with the bending mode, the twisting modes of deformation. Now you apply the voltage. So you will get the bending as well as twisting modes of deformation. That is the actual one we'll be seeing in the flapping wings of the birds or the different creatures. So this is the finite element part we have done. Along with that finite element part, we have also carried out the experimental simulation part. Experimental study is very, very important. So whatever we are seeing, maybe it's feasible on this software tool, but practically we have to check. So you see that we are considering a single compliant frame, and then we are putting all the required component like stiffeners, copper strip over that. And this is the mechanical constant, stretching mechanism that we have shown here. Okay. So this is the actual stretching mechanism. And when we release this from the external mechanical constant, so we obtained a initial flapping configuration of the flapping wings. You can see. And when we orient the stiffener, we will obtain bending as well as twisting modes of the deformation. So you can see an interesting task. We start with the bending actuator, then we take it to the forearm gripper, dragonfly, flapping wing configuration. So this is an interesting simulation for you that we have carried out in the Abacus software. So what it is showing, in the left side, it's showing when we have the membrane and the frame and we release it. So it will try to obtain a configuration. Okay, that is this configuration and it will stop at this configuration. So what is happening when you apply the voltage to that? So it will try to go back. It will try to go back. If you keep on increasing the voltage, it will try to go back to its original. But there is a threshold limit because stiffness are being put it there. Material is also filling the resistance. So up to a certain range, it can go back. After that, it will not go. So if you apply the actuation like cyclic loading, so it will behave like this. So you can see this motion. So this is the interesting application of the DMEs that we are having. And we can implement them for various other applications. I will show you in a video. So give me a second. I will just play a video for you. Is video visible?
Yes, sir. Visual.
Yes, sir.
Sound is coming or not? Just quickly verify. Let me start and then we can verify.
Sound भी clear, sir.
Sound itna isme theek hai. That is not required. So you can see that's what I'm talking. This dielectric elastomer based minimum energy structure can be used in the satellite application for the aerospace and the different for gripping an object. So that is one of the application it is being shown here. So initially, when you have the pre-stretch and you release it, it will try to hold an object. And when you apply the voltage, it will go back. So initial deployment. So this is the people are also doing this, develop this type of structure, DMS for different application. This is like you can change the material of the different incorporated anisotropy and all this tip stuff to obtain the different configuration. So you can see. So here I have already told you we can vary the material of the frame. But as a most simplistic frame, you can take your transparent file that you are using basically in day-to-day life. That is PET material. But we have a specific PET material for that. And what you can see from this figure, the electrode, the active area are formed in the patches. So that is an experimental study also being carried out. If we form this electrode in the form of a patches, we obtain a very good actuation at the required places. Okay. Now, when we keep on increasing the voltage, it will go like this. So this is the PET material, PET frame that I am talking about. We can basically use when we plug in the voltage, it will go back. It will try to come back. You can see. You switch off the voltage, it will come back to this initial configuration. You keep on applying the voltage, it will try to go back. So if you have the cyclic voltage, you can see like this. It will behave like this. This is the ramp voltage is being applied. Now, if you apply the cyclic voltage, it can go like this continuously. So this is a 3-arm gripper that is developed based on this DEMES. This is the cyclic actuation. So if you have the cyclic actuation, it will try to come like this. This is the hand, very good concept. So people are nowadays working on this concept that we can replicate the motion of human hand by using the concept of this DEMES. And recently we have got one project also. So in this, we are developing a soft gripper for the DRDO basically. They are requiring a soft gripper to be developed for them. So we are working on that project also. So I hope you like this video. I will come back to my PPT now. So just a quick coverage. What we have done, we have started with the dielectric elastomer and we implement in the DMS application. We start with a very simple bending case, bending actuator, analytical formulation. Then we extend it to by incorporating stiffener, we avoid the warping. Okay. Then we carried out the experimental part, and then we have taken it to an advanced application like gripper, flapping wing, dragonfly prototype by taking with the help of the finite element simulation. Okay. So yeah. Thank you. So you have any question now? We have a 5-10 minutes to discuss quickly. Yeah, please tell me.
Yeah, thank you, Professor, for a nice presentation. Now it is the audience. If you have any question, you can ask freely and you can discuss.
And we have our lab, Smile Lab, very interesting name, Soft Active Material Investigation Lab for the engineer. So any of you, if you want to come here, just give me a quick email, or over an email we can discuss anything if you want. So you can go to my lab website also.
Wow, good. It's a very good name.
Thank you. So yeah, please, any question. अगर आप, if you, मेरे को लगे कुछ समझ में नहीं आया, या तो सब समझ में आ गया, कुछ समझ में नहीं. So
No,
please
actually,
ask
the
questions.
audience,
Yeah.
audience is mostly the MTech PhD, and they are, of course, they are getting for the first time. So that is why. So they are, I mean, they are just grasping the ideas and all this.
That's why. I have put a lot of graphics and to be shown that how basically the application oriented. So you should be. I am telling you all during my observation in the foreign visits. I always get this idea. They are working on the prototype. So that is the major thing. Even this culture, we have to take it, and we are start taking that thing also here. They are basically doing. They are start having a problem from the beginning that they have to develop some prototype and supply them to some industrial practical application that will be for the social welfare, something like that. They have this problem definition in their mind, and they always keep on trying to develop some prototype. So that is very, very important. We always think about a problem that should have some physical impact or practical application. That will be very good for all of us.
Yes, yes.
Yeah. So any query?
Okay, if there is no query, then I'm having few.
Yeah, sure, definitely.
Yeah. So actually, it is a very nice presentation, and I think you have given the aspect. Actually, the previous speaker, some of the previous speaker, it was mostly the mathematical. You have given the mathematics as well as the experiment, which is I mean, it makes the entire package a very beautiful, very, very beautiful.
Thank
So
you so
now
much, sir.
I'm having this question that you are talking about the structure in the angular actuation that you have shown, or the finger that you are swaying. So over here, I really want to know that these, yeah, for example, this. So over here, how these finite element methods you are applying, because over here there are two material, and one is like, for example, the your nonlinear material, and on the other side, I think you have taken the that structural part as
Yes.
the metal or any conventional material which are of linear.
Yes. So,
So
sir, that's a very good question. That is the thing where we have. So initially we have one hyper-elastic material model that is for the membrane. We are having initial for that. So if you see, we have implemented the Gantt model of hyper-elasticity. Okay.
okay,
So if we put the value we are having our parameter to play with is the shear modulus. Okay, you know thing. I think you know that thing. So for the hyperelastic material, we have some particular definition of the shear modulus. We have particular value of that. But if we increase that value of the shear modulus to a very high value, so what we have done basically for the simple conventional linear material, we have defined the value of shear modulus in a large extent. And for the hyperelastic material, the same that we have considered. So from by considering the same material by varying the material property in the material itself, like a shear modulus, we try to incorporate these both material together. So
Okay,
I hope
okay,
I
okay.
hope it making sense.
Yeah. I'm understanding.
because
Actually, this
because that is the right
numerical.
question. Yeah,
Ha.
numerically, yeah. If you have one non-linear material integrated with the linear material, the entire figure or the entire configuration, if you are formulating finite elementally, it becomes very complicated, and your solution will not converge. That K matrix that you see.
Yes,
So
yes,
in
yes,
order to
yes,
get
yes.
rid of that, we have play with the shear modulus of the materials.
Okay. Yeah. So it's a very nice work, and let's thank the speaker for his nice presentation. And do you have any other question? You please feel free because we
So
have
may
five
I
minutes
ask?
time.
Yeah.
Yes, please.
Yeah, please.
So this is Atul. Okay, so I was having one question regarding this gripper part. Okay, so you said that for a particular application, so you have this cyclic kind of loading. Okay, so these materials having viscoelastic effects. Okay, so you will not have a same kind of a configuration for each cycle. Okay, because
Yes.
of this hysteresis. So in
Yes.
a particular application, how you will like take care that part for gripping a certain object. Okay, so
Very good question.
because this
I
viscoelastic
am
effect will
anticipating this question.
play very important role because you will
Yeah,
not
I am
get
anticipating.
the same configuration for a same applied voltage. Okay.
Yes. I'm anticipating this question. So there are two different ways. First, I will tell you. If you see in the market, the dielectric elastomer, there are different type of material for this dielectric elastomer. One is the acrylic elastomer that have a strong viscoelastic behavior. Okay, that is VHP membrane that we are using initially also, and there is a silicon elastomer is being there. Okay, that is also a dielectric membrane. So that silicon elastomer basically it will not have this viscoelastic behavior. That is a one thing. Second thing, in case of a acrylic elastomer that we have used here, so we can have the stress relaxation period. So you see here, initially we have the pre-stretching of the membrane, okay, this dielectric membrane. So we don't, after pre-stretching, directly put all this stuff, okay. So we wait for a 24-hour stress relaxation. So initially we provide 24-hour stress relaxation so that after getting stress relaxation, then we incorporate all this thing. So when we are taking into account the effect of stress relaxation, we have tried to, that is the one way of overcoming that. Then second way is we apply the voltage in a very like 50 volt per second like this in a very small way. So that is the other way to mitigate this viscoelastic effect. So there are definitely there is a challenge. One way you can have the silicon elastomer, you can go for that. It will not have a significant viscoelastic effect. Second way is if you are using an acrylic elastomer because it is giving a very good actuation. So you can do, you provide first stress relaxation. So if you are giving a stress relaxation of 24 hour, then it will have a very less viscoelastic effect and apply a voltage in a very small quantity, like 50 volt. They keep on increasing that voltage. So that will mitigate the viscoelastic behavior in the this acrylic elastomer. That is the two ways to overcome this issue. I hope you understand or I am making sense for that.
Yeah. So for a quasi-static loading, it is fine. But for dynamic loading, viscoelasticity will be playing very important role because while gripping, we need like a, quick grasping as well as this precise grasping as well. So for quick one, then we that viscoelasticity will be the problem. But it's fine
Yeah.
for like for quasi-static loading. Yeah. So viscoelasticity will not be affecting the actuation performance.
I understand. So that's why we are also looking for this. Initially, during our study, also we faced this problem when we are carrying out experimental. So now we are also looking for the alternative option like silicon elastomer. I have already told you that they will have a less viscoelastic effect. The other way is if we can put some composite type of layer. If we put some oppo layer, like if we have one dielectric membrane layer, combine it with an oppo layer. So overall effective viscoelasticity we see oppo layer has a very less effect. So viscoelastic behavior. So when we club them together, So the overall viscoelastic properties can be controlled or it can be tuned down. So that is the other option we can look for that also. So we have developed in one of our composite study for that OPPO layer along with this dielectric membrane to control this viscoelastic property.
Okay, okay. Thank you. Thank you.
Thank you. Thank you so much. So thank you, audience. Thank you for patience listening. And thank you, Professor Somnath Sarangi and Department of Mechanical Engineering, IIT Patna, for giving me this opportunity to interact with all the young minds of our country. Thank you so much.
Thank you, Dr. Aman. And so we are having only 1 minute of time, and our next speaker is already there. So let's not to wait. Let's welcome Dr. Atul Kumar Sharma from IIT Jodhpur. And I think I have introduced all the speaker on the very first day. So there is no need of formal introduction, and we'll be just going directly to his talk. So now, Dr. Atul Kumar Sharma, the stage is yours. So please. Uh,
Okay, so thank you, Professor Somnath,
thank
for
you.
invitation, for delivering a talk in this workshop. So let me share my screen. So let me know, is it visible or not? So just okay. So can you see my screen?
Yes, sir. It is visible, sir.
Okay, it is. Okay, so thank you. So So I will be talking about the modeling of soft dielectric elastomers. So on most of the things like a motivation and introduction is already covered by Dr. Aman in the previous talk. So I will quickly introduce soft dielectric elastomers and their potential application already covered by Dr. Aman, and then I will move to the an energy based approach to derive the governing equation for soft dielectric elastomer based actuators and the motivation behind finite element modeling. So what are dielectric elastomers? Dielectric elastomers are nothing but the you can say that polymeric film. So this is a polymeric film which is sandwiched between the compliant electrodes. And if you will apply the potential difference, what will happen? There will be accumulation of a positive charge and the negative charge on the opposite surfaces. And because of this positive and negative charge, there will be a Coulomb force, and which will try to squeeze this polymeric film. And because of this, there will be a lateral expansion and of the membrane. So here we have, because of this applied potential difference, we have a mechanical deformation. You can see here. So we have this single element simulation or finite element simulation of a dielectric elastomer block. So initially we have a cubic block, and if we apply a potential difference, and because of this positive and negative charge on the two surfaces, you can see that deformation, how this polymeric film will expand laterally and undergo contraction in the thickness direction, or the direction in which we are applying the potential difference. And this is the like a experimental one. So here we have a compliant electrode, and then you can see that expansion of membrane in the lateral direction, and anyway there is also a contraction in the thickness direction. Okay, so these things has already been covered by the in the previous talk, so I'm not going into the detail. So here if we talk about the applications, one is that in a soft robotics you can see that a gripper. So these grippers, this conventional gripper can be replaced by the soft grippers, or like so here if you see that if we want to mimic the elephant trunk like motion using this conventional robots. So we will be requiring n number of links or more number of links to mimic such kind of a motion. And if we have a more number of links, then control of each link separately will be also a difficult. Okay, so but if we use this dielectric elastomer, that single link can achieve the this elephant trunk kind of a motion. Okay, so that is the main advantage. So this hard machine can be replaced by soft machine and easily. But there are certain other problems as well. The, for example, load carrying capacity and all those things are limited in the soft grippers as well. Another if we see that if we are using this conventional robot for grasping the, let's say, fruits, so what will happen, these the metal kind of a gripper can also damage the fruits. But if we are using these soft material based grippers, then it can achieve the it will not be like damaging the fruits. Okay, they can achieve the shape of the object as well. Other application, you can see that in a biomimetic actuation. So here this mimics the facial expression of a human, as well as the, if we talk about lens, so if we have a conventional lens, once it is manufactured, its focal length is fixed. But if we are using this soft material, we can have a variable focal length as well. Okay, and there are other applications, like you can say that in swimming, as well as this crawling robots and that walking kind of a robots. Okay, these things has already been covered, so I'm not going into the detailed discussion of these things. But so I will be talking about a very simple any energy based modeling approach for deriving the governing equation for dielectric elastomers. In particular, I'm interested into uh, deriving the relationship between the applied potential difference, that you can say that if I apply a potential difference phi magnitude, that phi voltage, then what is the corresponding contraction of this film or the expansion of this film? What is the relationship between this phi and the corresponding deformation, let's say displacement du? Okay, that analytical approach using energy based approach, I will be deriving that part. So uh, so before that, so we will see a simple case that all of you are aware. Let's say if we talk about a linear elastic spring, so that we can create a motivation behind using the energy based approach for deriving the equation of motion for soft Ds. So let's say if you have a spring, a linear spring with a constant K, let's say if I apply a force F at this end, so what will be the displacement of this end? So that is, let's say, U. So for corresponding to the applied external force F, the displacement is U. So what is the relationship for the linear elastic springs? Okay, so can be obtained this the relationship between F and U using the energy based approach, or that in particular I will be applying the principle of minimization of potential energy concept. Okay, so first of all, tell me what is the relationship between F and U for this case? Can anyone answer? If it is a linear spring and within the elastic limit, if we talk about what is the relationship between F and U, you have already studied this problem in the 12th standard or the 10th standard as well. Okay, so you know that F is
F
equal
equals
to
to Ku.
K into U, where K is the stiffness of the spring. Okay, so can we derive this expression using the energy based approach or the principle of minimization of potential energy? So that we will see first, and the same thing on the parallel line, we will be understanding the modeling of these dielectric elastomer system, which is a nonlinear, uh, which has a nonlinear material behavior. Okay, as well as they undergo large deformation. But the, if we talk about the steps in deriving the voltage and displacement relation, will be same as that we will be following for the spring and force system. Okay, so now tell me what is the energy stored? For example, if I stretch this spring by displacement u, okay, so what is the energy stored in the spring? So that we call as a strain energy. So if we talk about the strain energy or the energy stored in the body or this system will be nothing but half k into u square. That is the energy stored in the body or the system or a spring. And if we talk about the work done, okay, work done by the force, or that we called as a, we also consider work potential, okay, that is the negative of the work done by the applied external force. That will be nothing but minus f into u. Okay, that will be the external work, no, work done, and this is the energy stored in the body when it undergo displacement of a magnitude u. Okay, so now if we talk about the potential energy of the system, total potential energy of the system, which is nothing but the sum of the strain energy and the work potential. Okay, so if you see that the total potential energy of the system will be nothing but half ku square minus fu. So this is the total potential energy of the system. Now we will apply our principle of minimization of potential energy in order to extract what is the relationship between F and U. So principle of minimization of a potential energy says that the stable equilibrium will be corresponding to the or the stable equilibrium deformation will be corresponding to the minimum of the this quantity, which is the potential energy. If we talk about equilibrium only, then it may be maxima or minima. Okay, so unstable equilibrium is corresponding to the maximization of the potential energy, and the stable equilibrium position or deformation configuration is corresponding to the minimization of a potential energy. Okay, so for a stable equilibrium we will say that this or other, for extremum, that may be corresponding the first condition for the maximization or minimization of a quantity is nothing but the first derivative of this quantity should be 0. So that will be, we can write, because it is a single variable problem, so you can say that dp of du will be 0. So this will give you, so if you take the derivative of this with respect to u, that will be ku, and that will be minus f. Okay, so this will be the first derivative, and you can say that we have to put it equal to 0. So from here you find out that ku is equal to f. So this the same expression that we know uh, for this spring force system, but I said that it should be corresponding to the minimization of potential energy. Then we can say that the deformation state is corresponding to the stable state, otherwise it is corresponding to the unstable state. For that, what we have to do, how to check whether this u value, which is f upon k, is corresponding to the maximization of minimization. How to check whether this outcome, which is u, is corresponding to the maximization or minimization. So for that we have to take the second derivative of your function. So that will be d2 over du square of pe, and if you see that this is nothing but the, if you take the this is the first derivative, and if you take the second derivative, that will be k. And you know that the stiffness of the system is nothing but the always positive. So it means that the whatever relation that we have derived is corresponding to the stable equilibrium, okay, of the system. So this is how we derive the force displacement relationship for spring force system using energy based approach, or the principle of a using principle of a minimization of potential energy. On the parallel line, we will be deriving the relationship between this applied potential difference phi and the corresponding deformation level, how much it is under, how much is the contraction of the film, or how much is the expansion of this film. Okay, so that we will be deriving. So for deriving that, what are the quantities required? That is the work done by the forces. Here, what is the force? External force. That is the applied potential difference. Okay, that is doing the work, or you can say that you are attaching it to some battery and there will be battery work. Okay, uh, and there is no, you can say that applied mechanical load. So I'm not considering the mechanical load. We can also pre-stretch it using some forces. Okay, but I'm going to derive only the relationship between this voltage and the corresponding deformation. Okay, so but I will be making some assumption for deriving that relationship. So let's consider, so I am creating the geometry for which I want to uh, develop the uh, equation of motion. So let's consider that so I'm considering this kind of a geometry, a planar geometry. Okay, so this is a, you can say that a dielectric elastomer, or it is a membrane, you can say that. And if I and it is pasted with a compliant electrode on both the sides and the top surface and the bottom surface, and which will help you to apply the potential difference. Okay, so now let's consider that the dimension of this geometry that we have considered are like this. So this dimension is L, this dimension is also L, or you can say that planar dimensions are L, and the thickness direction, that is H. Okay, so this is a geometry I have considered. You can say that a cuboid kind of thing. So which has a two dimension L, and the other direction is H. Now what will happen if we apply a potential difference? Let's say if I apply a potential difference through the thickness, or I am applying, so you can say that this will be one surface and another surface is this bottom surface. So now let's say this applied potential difference is phi, and because of this it will undergo deformation. Means now if it is undergoing deformation, then the now dimension will change. So now thickness will be having will be will reduce, and the L will also increase. Okay, so and I'm assuming the assumption of that membrane is undergoing homogeneous deformation. What do you mean by homogeneous deformation? If you consider each and every point, okay, on this surface, you can say that uh, the change in the thickness is same. Okay, so whatever thickness will be at this point, that will be also at this point, or any point if you will consider on this plane, then the thickness is constant. Okay, so and also so now let's say when it undergo deformation, the deformed configuration is like this. Okay, so it will, as I said, the it will expand in the parallel in the lateral directions, and the thickness will be reduced. Okay, so I am considering that when it undergo deformation, so thickness has been reduced. Okay, and the planar dimensions has increased. So let's assume that this becomes small l, and this becomes small h. Okay, so earlier, before application of a potential difference, okay, so this I'm applying here. So its dimension was L, capital L, capital L, and capital H. But when we apply this potential difference phi, okay, so this is the deformed configuration. So its dimension become small l, small n, and small h. So now I'm defining the quantity or the relationship between the dimension of this object in both the configuration. Let's assume that
dimension, let's consider, if you consider the, let's say, the coordinate axis as well. So I can now let's say that x1 is this direction, this is x2 direction or planar direction, and thickness direction I am considering, let's say, x3. Okay, so now let's assume that the relationship between the dimension of this object in three direction is like that. So let's say small h is nothing but a quantity lambda 3 times of capital H. So if you know lambda 3, then you can find out that what is the deformation in or the contraction in the thickness direction. Similarly, I am writing L, let's say it is lambda 2 times capital L, or this is nothing but a L, or we can say that because of this symmetry of the object or the symmetry of the configuration, we can say that the contraction in the x1 direction as well as the x2 direction will be same. This will happen when your geometry is symmetric, because we have taken the x direction or the dimension of this object in the x1 as well as x2 direction is same. That's why the final dimensions are also same. So you can say that it is nothing but, I'm writing it as a L is equal to lambda times capital L, and this L will be also same, lambda times capital L. Okay, this is one assumption that or the I have taken, that our geometry is symmetric in the you can say that in x1 and x2 direction. So that's why we have a lambda, which is the, we call it a stretch parameter. Stretch parameter, which is defines the ratio of the dimension in the deformed configuration to the undeformed configuration in the principal direction. Okay, so that is L upon capital L, or you can say that lambda 3 is your small h upon capital H. So this is how we define the deformation, how the your dielectric elastomer will undergo deformation, or you can say that this defines the kinematics. Now another assumption that we are making is that your material is incompressible. What do you mean by incompressible? Incompressible means the volume of this uh, uh, dielectric elastomer will remain unchanged. Okay, whatever deformation we are having, volume having in the undeformed configuration, that will be as same as for the deformed configuration. So if you compare the volume, so before deformation, what is the volume? That will be nothing but, it is a cuboid, and the volume of a cuboid will be L times H. That will be capital L square H. After deformation, what it will be? I am writing it as a capital V. So that will be nothing but small h, small l into small l. So that will be, and small l square times h. And now you can represent, you know that how h is related to capital H and how small l is related to capital L. So we can say that it will be uh, small l square will becomes lambda square times l square, and h will become lambda 3 times capital H. So now if you apply this incompressibility constant, that is V is equal to V naught, means the volume will not change while during deformation. So this will make you to the lambda square lambda 3 L square H is equal to L square H, which will say that, so L square H will be cancelled out. So from here you can say that we have a relationship, that is lambda 3 is equal to 1 upon lambda square. So now we can say that lambda 3, which is uh, uh, the stretch in the thickness direction, can also be represented in terms of lateral stress, that is lambda. So now we can say that what is the deformed configuration of the body. So I'm creating it again. So just a minute. Just a minute, I'm recreating it. So just what is it? Okay, so I'm recreating it. So let's say this is now your final version of the configuration, deformed configuration. So I can like this. So this is this dimension, that lateral is nothing but your lambda times L. This is also lambda times L, and this thickness direction is, you can say that, write it as a H times lambda 3, which is nothing but lambda square. So now you can say that the volume of this volume in the deformed configuration is again L square H, and also for this undeformed configuration was L square H. But now one thing is that is not known to you is that the quantity stretch lambda. Once you know lambda corresponding to that applied potential difference, that is uh, phi. So we have the relationship between this phi and lambda. Okay. So now we are interested how this phi is related to lambda. Like for spring force system, you have a F, how it is a function of U, that we have already derived for a spring force system. That was linear relationship, F is equal to Ku. Now we will see what is the relationship between this phi, which is applied potential difference, and this stretch lambda. For example, let's say phi is having value 2 kilovolt and lambda comes out to be 1.2. So then you can say that for a 2 kilovolt applied potential difference, the dimension will becomes 1.2 times of initial dimension in the lateral one. And the corresponding dimension, you can also calculate what is the contraction in the thickness direction as well. So we will see how to derive it. Okay, so for that, so I will be talking about, first of all, in order to calculate the total potential energy of the system, we need the strain energy or the energy stored in the body and the work potential. Okay, if you see this equation, this is same as that we applied for the uh, spring force system as well. Now, if we talk about energy stored in the system or energy stored in this uh, the dielectric elastomer, there will be two kind of energy. One is the energy due to deformation and also the electrostatic energy. Okay, if you talk about parallel plate, so if you see this system is same as that of you have studied parallel plate capacitors. Okay, you have a two plates, metal plates, and in between of that you have a dielectric material. Okay, so if you see that what is the energy stored in the body or this parallel plate capacitor or the electrostatic energy stored, that is, you know, that half C into phi square, where C is the capacitance and phi is the applied, you can say that, potential difference. Okay, same concept we will be applying, because here if you see this configuration, that is same. We have electrodes like parallel plates, but here we have a compliant electrode, it undergo deformation. Okay, and we are not having rigid electrodes. Okay, and but if you see that in between of those electrodes we have a dielectric material. Okay, the configuration is same, and it is a case of a parallel plate capacitor. And you should you know what is the capacitance value for the parallel plate capacitor. Okay, so that we will apply here. So here if we talk about the strain energy components, we have a two component. One is the elastic energy, you can say that elastic part. Another one is the electrostatic part. Okay, we will see what is the energy stored, okay, in the system, and another is the work done. If you see, the work done is only because of the applied potential difference which we are applying through, let's say, battery. So that will be nothing but the because of the battery work. Okay, so first of all we will talk about the electrical part, what is the work done by the battery, and what is the energy stored or electrostatic energy uh, stored in the dielectric body. So if you talk about battery work or work potential, how is the battery work? That is nothing but Q, which is the charge, into phi, which is the voltage. And you know that charge can be also written in terms of a capacitance. So that is nothing but C into phi. So these are the relationship that you have studied during your 12th standard. Okay, when you in a physics you have studied the capacitor chapter. So it will be work done by the potential energy, work done by the battery will be nothing but minus, if you put it here, that will be minus C into phi square. That is the battery work or the work potential required for the writing the total potential energy of the system. Now, if we talk about the electrostatic energy stored, okay, so that will be nothing but, what is that quantity? If we talk about is energy stored in the system for a parallel plate capacitor, that is nothing but half CB square. आपने पढ़ा होगा. So that is here C phi square, because we are representing voltage by phi. This expression hopefully you have gone through, that half CB square or half C phi square, that is the which is the energy stored in the capacitor, parallel plate capacitor, any capacitor, because we have not defined the C for a case of parallel plate. So if we talk about the work potential is minus half C phi square, energy stored is half C phi square. Okay, so now tell me, for a parallel plate capacitor, what is your C? Because we want to establish the relationship between only the, because phi is known to you because you are applying to the system. Okay, so we know what is the applied voltage potential difference value, for which we want to just establish the relationship for the phi and lambda. So now we have to replace this C by the known quantity. Okay, so now if you see, for a parallel plate capacitor, C is nothing but your epsilon A upon H. What is epsilon? Which is the material parameter, that you know, dielectric permittivity. What is A for a parallel plate capacitor? That is this surface area. And H is the gap between the two electrodes. Or you can say that here the thickness of the dielectric material, that is small h. So now if you talk about the area, so that will be your epsilon. Area will be nothing but your, what is your area? Surface area will be lambda L times lambda L. So that will be your lambda square L square. What is your H? H, if you will see, that is your thickness, that is capital H upon lambda square. So this will become epsilon lambda to the power 4 L square upon H, which is your C. which is now we have written in terms of a known parameter, because this is the material parameter. Dielectric permittivity, L and H are the geometric dimension of the elastomer. So you will be aware about what is the dimension of this elastomer that we are taking in the and before application of applied potential deformation. Okay, so this is how we can write C. Once you know C, you can write your work potential L as well as the energy stored in the system. So that will be your half. If you talk about sum of these two quantities, which is the sum of the work potential and the electro, because here if we need sum of the three quantities: elastic energy, electrostatic energy stored, plus work potential. So sum of these three will give you the total potential energy of the system. So out of which the sum of the two quantity, which is the electrostatic energy stored in the system, or you can say that strain energy, that is electrical part, plus or electrostatic energy stored plus work potential, will be nothing but half C phi square minus C phi square. So that will be minus half C phi square, and that can be written as your minus half C is your epsilon lambda to the power 4 L square H, which is your C, and phi square. So this is the expression for the summation of a two quantity: electrostatic energy stored in the body and the work potential. Now one quantity is remaining, is nothing but your elastic part of the strain energy. So for this kind of a material, which is you can say that rubber kind of a material. Okay, so in order to model the rubber, we use a hyperelastic material model. So I will be considering a simple case, which is the Neo-Kean material model. Okay, even if we talk about a axial bar. Okay, so for axial bar, if we talk about uh, for a linear elastic solid, okay, in a linear elastic solid case, what is the how to write the strain energy density or strain energy? If for example, if you consider a 1D case, you write it as a energy stored in the system, that is nothing but half sigma x into epsilon x, where sigma x is the normal component of a stress and epsilon is the strain quantity, which is nothing but the strain energy per unit volume. If you multiply it with the volume of the your system, which is axial bar, let's say it is having cross section area A, length L, then if you multiply it by A into L, then you will find out the total energy stored in the system, or strain energy for this case. So what quantity is required to define the total energy stored in the system or the elastic energy is nothing but the strain energy density, which is the strain energy per unit volume. Okay, so I have directly written this A into L because sigma and F is constant, and so but so but one thing is that is required is strain energy density. For if we talk about, you use Hooke's law, and the energy density is nothing but half sigma into epsilon for a 1D case. But here, because this is not a linear elastic solid, this dielectric elastomer is not a we cannot model it using a Hooke's law. We have to use some other model, out of which one is the Neo-Kean model or hyperelastic model. For such model, the energy density, which is nothing but the energy stored in the body per unit volume, that psi for our case, which is the where we have considered the that material is incompressible, This strain energy density is nothing but in this format. Mu upon 2. I will tell you what are the parameters. Lambda 1 square, lambda 2 square plus lambda 3 square minus 3. Okay. This is the expression for the strain energy density for a dielectric elastomer that we have considered. What are lambda 1, lambda 2, lambda 3? These are the stretch values in the three principal directions. Here the three principal direction is x1, x2 and x3. So what is the stretch in the x1 direction? That is lambda. What is the stretch in the x2 direction? That is also lambda. What is the stretch in the x3 direction? That is lambda 3. So we can insert those values here. So that will give you psi as mu upon 2. In the x1 direction is lambda square, x2 direction is also lambda square, and x3 direction was 1 upon lambda square. So that will become 1 upon lambda to the power 4 minus 3, which is the energy stored in the body per unit volume. And your mu is nothing but your, again, material parameter, that is shear modulus. Okay, so you can search this Newton model and then you will find out this expression anywhere. So once you have this elastic energy, then we can write out the total energy stored in the system. That will be nothing but, like here we are writing, this is the psi function, that is strain energy density. If you multiply it by the volume, then you can find out the total energy stored in the system for an elastic bar. For example, it undergo, let's say strain is epsilon x. Okay, it will be vary because it is a point function. We define at a point. So total energy stored in the system is nothing but energy density times the volume. So similarly, now tell me what is the volume of this your system, dielectric elastomer. So it is nothing but your L square H, and it is not going to change throughout the deformation. At any state of deformation, it is L square H. So we can say that energy stored in the body will be your psi times L square H, which is the elastic part. Okay. And you know what is your psi. Psi is your mu by 2. So now all the three components are known to you. So for writing the total potential energy of the system, you have to know about the elastic part that we have written recently. Another one is the electrostatic energy stored, that is half c phi square, and the work potential, that is minus c phi square. You know all the three quantities now. Once you have these all three quantities, you can write the total potential energy. So the total potential energy will be nothing but your, I'm writing now, that is the L square H times psi, which is the elastic part, and the sum of the last two quantities, which is the work potential and the stored energy, electrostatic energy stored, is nothing but minus half c phi square. That is this one. So that is minus 1 upon 2 epsilon lambda to the power 4 L square upon H into phi square. And I can write psi as well, so that you can take L square H common, so that you can write it as a psi, which was mu upon 2 lambda square plus lambda to the power minus 4 minus 3. So I've written just this expression. So lambda square plus lambda square will be 2 lambda square, and 1 upon lambda to the power 4 we can write lambda to the power minus 4 minus half epsilon. If you take L square H common, means I have multiplied H and H on the numerator and the denominator as well. So we can say that it is nothing but, just a minute, I will check what is happening. Okay, so that is nothing but your lambda to the power 4 phi square upon h square. Okay, I have taken this quantity outside the bracket. So this is your total potential energy. Now, what principle of minimization of potential energy says? The stable equilibrium will be corresponding to the minimization of uh, this potential energy function. So now, for even maxima or minimization, you will be having the first derivative of this. So what is not known to you? What is your function? The unknown variable here. Tell me, like for a spring force system, your u was not known to you. For dielectric elastomer, what are the quantities in this expression? That is a variable or your unknown variable. So mu is known to you because it is a material parameter. L and H are also known to you. Epsilon is also material parameter. Phi you will be knowing. What is the applied potential difference? Like force in the spring force case. So the quantity that is not known to you is a lambda. So you can take the derivative of this function, potential energy, with respect to lambda and equate it equal to 0. And if you do that, let's see what we are obtaining here. So that will be, if you take the first derivative, that will be mu upon 2, which is a constant, and it will be 4 lambda minus 4 lambda to the power minus 5, and 3 will be 0, and derivative of 3 will be 0, and minus epsilon upon 2 into 4 lambda q phi square upon h square. That should be equal to 0. So now we can say that 4 you will cancel out. L square h will also go on the right hand side. So 0 upon L square h will be 0. So here you will find out, and 2 will also cancel out, because that, or you can say that will go on the right hand side. So that will become 0. So you have an expression like mu lambda minus lambda to the power minus 5 minus epsilon lambda q phi square upon h square is equal to 0. Or you can say that phi square upon h square into epsilon upon mu will be equal to, you can take the unknown terms on the one side and the known terms on the other side. So I have taken all the known terms in this equation on the left hand side, which is phi, epsilon, h and mu from this equation, and on the right hand side it will become, so lambda q will come on this side, so that will be lambda to the power minus 2 into lambda to the power minus 8. Or you can write, because here it is a square term, so you can take the square root on both the sides. So this will become phi upon h square root of epsilon upon mu is equal to square root of lambda to the power minus 2 minus lambda to the power minus 8. So this is the expression for the relationship between the applied potential difference phi and the your deformation parameter, that is a stretch, how much your elastomer has stretch in the lateral direction, that is lambda. So here one thing that you will observe, that the relationship between phi and lambda is not linear, like for a spring case F is equal to Ku, that was a linear relationship, but here you will find out a non-linear relationship. Another point that I want to tell you is that this relationship is uh, uh, corresponding to the any equilibrium. It may be corresponding to the stable equilibrium or may be corresponding to the unstable equilibrium. Okay, because here we have taken up the first derivative only. So now you can find out what are the values of lambda for which the second derivative of this potential energy is positive, and for what value of a lambda it is negative. Okay, so that you can say that this branch of the response is corresponding to the stable equilibrium, and this is corresponding to the unstable equilibrium. So now what I'm going to do, I'm just plotted this response or this equation. How is the, you can say that for a applied voltage, what is the corresponding stretch or the deformation level. Okay, you know that if I apply for a spring force system, if I apply 10 Newton force, and if you know K, then U will be your, or deformation will be F upon K. Similarly, now if I say that if I know material parameter for if you consider a real case, let's say for a that in a previous talk Aman talked about BHB tape, for which let's say epsilon is 4 times of a epsilon naught, and shear modulus is let's say 30 kPa or 40 kPa, whatever you value take, and let's say the thickness of that BHB is before deformation is let's say 1 mm. And then if you are interested to know for a given voltage or applied voltage of let's say 1 kilovolt, what is the reduction in the thickness, or what is the lateral expansion. For example, here in the GIF if I have shown, so if I'm here I'm applying potential difference, how much is the expansion for a given let's say 1 kV voltage, how is the lateral expansion, that you can find out, or for this case you can find out from this equation that we have derived here. Okay, so now if what I did in the morning, so I plotted this equation. Okay, so this is the response of the system. So what I did, I just plotted this non-dimensional quantity. If you see that, what is the unit of lambda? Lambda is the ratio of L upon capital L. L is also length, capital L is also length. And it means that this quantity is non-dimensional, is not having any dimension. So the left hand side, the quantity will also not having any dimension. So this quantity I am calling it as a non-dimensional voltage. Okay, so I plotted this quantity which is a dimensionless voltage to the stretch. So this is the response, and you can see that it is not a linear like your case of spray. But one thing that I missed is that I said that we have to calculate the second derivative of potential energy as well. For what value of a lambda it is positive, and for what value of a lambda it is negative. So this is the critical point. Okay, so where the slope of this curve is 0. You can say that so here in this region, so I can now bifurcate. This is the reason, or you can say that this voltage stretch value is around I know I calculated is 1.259. This value is nothing but the second derivative of PE, that is potential energy with respect to lambda, is nothing but your positive. And in this region it is negative. Okay, so means that this graph till 1 to 1.259, your deformation is corresponding to the stable equilibrium, and the other part is corresponding to the unstable equilibrium. It means that this is the value of applied voltage, which is nothing but the value is nothing but around 0.687. Okay, this is non-dimensional quantity. Okay, so you can calculate actual voltage by just uh, putting the values of your epsilon, mu, and h. What is the critical voltage? So this is the critical voltage that you can apply to the system in such a way that its deformation is corresponding to the, you can say that, a stable equilibrium. Okay, so what will happen after this point? Let's say if you go ahead with a example, let's say this is the value of a point of applied voltage 0.687. Now if you apply the value above that 687, let's say 688, what will happen? What is the deformation level? If you go above this, it is infinity. It means that your thickness is going to be zero. Or you can say that there is a, after this value, there is a sudden decrement in the or reduction in the thickness. Or what will happen in actual practice? It will break, it will fail because of the dielectric breakdown. Okay, if your voltage is above than 0.687. So you can say that this is the operational range. So your dielectric elastomer will work if you have a till, so that will undergo deformation level of a 1.259 stretch only if we are modeling it using Neogen model. And but the voltage that you can apply, that is a non-dimensional voltage, will be 0.687. After this it will fail. Okay, so this is the operational range for your dielectric elastomer. Okay, so you can say that these are the critical parameters that you can also directly extract. So now tell me, what is the value of a second derivative of a potential energy at this point? I'm talking about critical point. What will be its value at this point? What is the second derivative? So I'm saying that in this side it is positive, on this side it is negative. Let's say if you are going from 2 to minus 2. Okay, so there will be a point where it is taking value 0. Okay, you can say that it is positive when it is greater than 0, it is negative when it is less than 0. So at the critical point the potential energy will be 0. So you can also extract your what is the critical value directly without plotting this graph, just by solving the two equations, which is the one equation is this one, the first derivative of a potential energy equal to 0, and the second derivative of potential energy with respect to lambda square is equal to 0. So you can directly find by solving these two equations, non-linear algebraic equations, you can find out your two unknowns at that point, critical point. That is nothing but what is the critical stretch as well as the critical phi value. So that I'm saying that values I have calculated. I said that its value is a 0.687, which is corresponding to the, you can say that phi value, and this is the lambda value. So you, these two value you can directly find out by just solving these two equations as well. Okay, you can say that these are the failure points for a dielectric elastomers. Okay, so so I'm not going ahead because now Aman has already told why we need finite element modeling. So so here that one assumption that we made was a homogeneous deformation. But in actual practice, if you see this mirror kind of things, okay, so I talked about focal length. So it is not a case of a homogeneous deformation. Even if you talk about this breakdown, dielectric breakdown, so or you can say that wrinkling patterns here in this case, if you see that before failure, you can see that some wrinkles formation. So the value of a thickness stretch at this point and this point is different. So we cannot model such cases using this approach that I have talked about. Okay, so that is a simple approach because I want to give, because I have gone through the different lectures, they talked about different cases, but I want to tell you like with us in a simple words how to derive the expression for this input and output relationship. Okay, or the voltage and displacement relationship based on like using simple approach. That was my motivation behind this talk, and then I did all those things during so like I wrote my own code on using MATLAB, and I developed certain computationally efficient model for finite element cases as well. Okay, so we have solved where will be the location of this dielectric breakdown and all those things in our case, and we have also done simulated this gripper kind of things, bi-layer grippers. So these are the finite elements results where you can see that the deformation levels so the deformation is not homogeneous. Okay, so you can see that the deformation at this point and this point is different. Okay, if we talk about contraction of the layers, so we have simulated certain cases earlier. So okay, so I am done, Professor Sarangi. So
if you have any questions, so we can discuss.
Okay, so thank you, Professor, for your this fundamental concept apprising the audience, and it is quite nice. So far, I think the speciality we are getting over here is that at first we have seen many such things which is quite unknown to the audience, and still they were in trust of getting the fundamentals, and you have addressed that fundamentals. It complements the entire thing. So I
Okay.
can expect many questions from the audience.
Yeah. So
Audience, please. Any question, audience?
okay.
Yeah.
So I think I have done like lots of mathematical part.
Actually, sir, what happened is that this workshop is full of mathematics. I mean, even if we want that mathematics should not be there, but
Okay.
mathematics is inevitable.
Yeah.
And fortunately, one speaker he used the list mathematics, and he gave the complete idea about this setup and all these things. So that
Okay.
way it is all right. Now to just to complement it, what professor has talked about the New Hookean model, right? Now, if you
Yeah.
are going to go to that that strain energy density function W is equal to mu by 2.
Yeah.
Yes, yeah, it is over there. So if you want to go the details of it, then you have to enter into the statistical mechanics. So
Yeah.
actually the thing is that mechanics is a very beautiful subject.
Yeah.
Well, you'll find that this is what is the subject. I think it is the only subject
Yeah.
which covers the entire zone of the our science.
Yeah.
It can vent to any section of it.
Yes. 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 Yes.
And that is what is the beauty of mechanics. Actually, whatever we are going to say about this soft robotics, this, that, actually
Yeah.
we only deal with the
Micromechanics. Yes.
mechanics only. And
Yeah.
that way, I mean, this is what is the new topic. So that way we went into that, and this
Yeah.
is what is.
So this is
So
your workshop is corresponding to your ANRF project.
my workshop is related to this soft robotics and all these things only. So
Okay, so this is
actually, it
part
is
you
a
said in the inauguration. This is part of SSR activity or something.
Yes, yes. Actually, sir, it is a SSR activity, means scientific social responsibility. That means we have to communicate the whatever the development that is been happening into this field. So that has to go to the students and different stakeholders.
Okay. Yeah, because I was also having SSR activity, but I paid to the some interns, so I was not aware that we can also conduct some workshop as well as a part of this SSR activity.
Yes, yes, yes. Actually, what I thought is that our means we spend much more of time in publication, this, that.
Yeah.
So why
Mm.
not to do whatever we are doing it? Actually, it is a very yay activity, but why not to give it to the students?
Yes, yes, yeah.
And I can see that many MTech students, PhD students are there.
Yeah, yeah, yeah. Yeah. So that may be from our. So I forgot to ask our student to register. So otherwise they can also go through
Yes, yes.
this
So,
concept.
sir, actually, it is been recorded. So, if you want, you can take the recording of these lectures,
Okay, okay.
and you can take this and you can refer to your students, and the even the students can take it and give it to the other students as well, those who are needing it. So
Okay.
that way, our this workshop is going to be effective. I mean, the
Okay.
purpose of the government is going to be implemented.
Yes, yes, yes. Yeah, yeah.
Okay,
Uh,
Professor, thank you for your time and giving us the enlightening this fundamentals. And it is a very nice presentation and a
Thank you.
nice and unique presentation. So
Thank you.
thank you. Thank you, sir.
Okay, thank you. Thanks a lot.
So the participants will be meeting at 3 p.m. sharp. And thank you for your patience. So we are going to meet at 3. Thank you. Thank you, Professor.
Thank you. Thanks.
Thank you, sir. So you are leaving.